Hello ladies and gentlemen, today I have something very interesting and very special for you. I accepted the challenge to implement extremely complex Android animation. And when I say extremely complex, I do really mean that. So just to remind you about the background, I'm kind of skeptical of all these claims that Jetpack Compose UI for Android makes implementing animations so simpler and so much productive, and there are all this stuff you can do with Jetpack Compose that you can't do with the classical Android view system. So I'm skeptical of that, and therefore I said on the social network, on my Twitter account, that I'm accepting the challenge. Give me your most amazing, your most complex animations implemented using Jetpack Compose, and I will re-implement them using classical Android views. To remind you, last week I published a video where I implemented these two elements. So one was this gradient text button, which frankly was a relatively simple element to implement. And then also this very interesting element where we have this kind of counter that has this state, and I can manage the state using plus or minus buttons and do all kinds of tricky stuff like this one, what you see on your screen. So all of that was implemented in the previous video, and I told you back then that this second element is a relatively complex element that was challenging to implement. Well, it came nowhere close to what we are going to discuss today. So let me show you the challenge that I accepted. So that's my challenge for today, implemented using Jetpack Compose. We see that we have a stack of cars on the screen, and I can grab any of these cars, and when I grab it, it elevates the respective corner, or I can just, fling a card and then it falls at the back of the stack. And of course I can fling multiple cars, throw them into there, and all of them fall at the back of the stack. Very impressive animation, and I'm going to re-implement it using Android views. Well, actually I've already re-implemented it using Android views, and now I will just show you what I've got. That's my implementation of the same animation using Android views. And just like with Compose, I can take the card and it elevates the respective corner of the card when I take it, and I can grab it around, drag it around, and if I don't fling the card, it goes back to its original position, but if I just fling it, then it rotates and falls to the back of this car's stack. Now, as you might notice, I also implemented kind of horizontal movement in addition to vertical movement, and that's just because I kind of didn't notice that Compose animation does not implement horizontal movement, so my animation is a little bit more complex than what we've had in Compose, but frankly, it's not a big deal. Okay, so I can take a card and I can fling it, and of course I can take multiple cards and fling them, and all of them fall back into the position just like that. All in all, that's the animation that I implemented using classical Android views. At this point, I would like to just quickly go over the source code implementing both of these animations in the Compose version and in the classical views versions, and then we will get to the metrics, because I personally think that you cannot discuss, like one framework is better than the other, one tool makes you productive. You cannot throw these things around as a professional developer without providing some proof, some metrics. So I gathered these metrics and I will share it with you shortly after we will review the source code of these implementations. So let's jump into Android Studio. We will start with the Compose implementation. I did not write it. I was given this challenge and the source code was already written. I just modified several parameters here to make this animation a little bit slower for you to be able to see what's going on there. In general, we have this swipeable cards composable, and it also uses this swipeable card composable and sample card composable. And here down we have this swipe to back modifier, and it implements actually most of the complex state and animation logic of this very complex animation, right? And of course, the cars themselves are kind of trivial to implement. That's not what's difficult about this element, not the implementation of these cars, but the difficult part is actually the animation and state management. So that's the implementation using Jetpack Compose. I must admit that it kind of looks neat, not that much code, but I don't like it nevertheless, because I just feel that I don't understand what's going on here. So I do understand what's going on with this UI construction, but once we get here, I find it very difficult to kind of see what's going on and understand how this logic works with all this nesting and also, this coroutine scope. Quite complex implementation, but it's quite complex element. So for what it does, it's actually very neat, even though I don't like it personally. Now let's see how Android Vue's implementation looks like. In my implementation, I have this view called card view, and that's just the card. So it's very simple, nothing really interesting here. It took me about 40 minutes to implement this card. And then we have this stacked cards view, which actually implements all the complex logic of this very complex UI element. And as you can see, it's really long. Total 580 lines. Well, not of code, but in total 580 lines. And there's a lot of things going on here, including animations, including state management. The most interesting part here, well, there are a couple of interesting parts here actually, but the most interesting one is the state machine. So we have, let me show you that. Where is that? Okay, we have this my card class, and this class represents a card that we see on the screen, and you can see that it gets card view as a constructor argument. So we have this card view that implements the UI of the card, but actually what represents the card on the screen is this my card class, and it has more properties. Now I could put all of that into card view. Of course I could do that, but then card view will not be reusable. And I'm all for building reusable components, and therefore this card view is a standalone card that I can potentially use in other places. And my card inner class of this stacked cards view is what implements the card that we throw around in this animation. And it has a state. Okay, so my card has a state, and the state is one of these enum class. So either settled or dragged or animate snap back. That's when you release the card without freeing it, and it just snaps back to its position. Animate throw, well, this one is self-explanatory, and we have this animate position shift. And this is the state that happens when you throw a card and different other cards in the stack need to change their position. So they animate to their new respective positions. So these are the states, and we also have this state machine to state. Yeah, this method to state implements a state machine that decides what we need to do based on the state, the current state of this my card class, and the new state, the next state that we want to transition to. So this is the state machine. This is the most interesting and actually one of the most complex pieces of this implementation. That's what took most of my time. Well, not most of my time, but a considerable chunk of the time implementing this very complex UI element. Another very interesting thing to notice inside the implementation of stacked cards view is that it overrides this onIntercept touch event method. Why do I need to override this onIntercept touch event and then use onTouch event, manually basically managing these events? And furthermore, I have this isPoint in view method. So basically when I intercept the event, I manually go and look for the card that needs to handle this touch event. Why can't I just, attach touch listeners to the respective card view and let Android do its magic? Well, that's what I did initially, but it didn't work quite well. I spent maybe 2 or 3 hours trying to make it work until I realized that it just won't work. So I refactored to basically translation Z. We have translation Z on these cards. Let me show you that. Basically here, update cards translation Z. So whenever the index of the card in the stack changes, I update its translation Z value. And that's what makes the cards appear before or after other cards. The problem with translation Z, and that's why I didn't use it initially, is that it does not affect the order of the click. So basically, even if you send the card to the background using translation Z, but its first child inside the respective parent view, this stacked cards view, then it will be the first one to get any interactions, any touch events. And that's what I tried to do initially and manage basically the order of these cards inside the parent view in order to kind of translate them back and forth, but it just didn't work out quite well. It led to all kinds of problems, and therefore eventually I had to just scrap it and refactor to using this translation Z. And since translation Z does not affect the order in which the cards receive touch events, I had to implement my own touch events handling and manually find out which card needs to handle each touch event. So that's kind of this part of the logic. Very interesting part that took me quite a while to figure out. But actually, once I decided to implement that, it took maybe 40 minutes. So I spent 2 or 3 hours trying to make the previous, basically children view based approach work, but it didn't work. So I just refactored in 40 minutes to this new approach using translation Z and put some comments here to remind myself why it works and why we need it. Okay, so there are Also, more complex stuff here, like for example, stack management, how we manage stack. And this is the way these cards handle touch events, various touch events. Here we compute all kinds of stuff. For example, when we release or cancel a touch event, then we need to decide whether we snap the card back or we throw it. And that's the logic that makes this decision. Basically, we need to make sure that the card is moving upwards because, well, initially I was able to throw the cards down, but actually that's not something that I wanted to have. So we basically restrict the throws to being in the up direction, and we ensure some speed velocity threshold. So we want to make sure that the user actually flings the card at some specific speed. And we also want to make sure that the card is somewhere above a specific threshold on the screen. And that's just, to make sure, well, I don't know why I added this, but it's there. I don't remember why, but it's there. And all kinds of other complex methods. And these are the animations. So we have this animation to default scale, and we have animate throw and transfer back. Quite a long method, a lot of animations going on here. We compute all kinds of rotations, scale, translations. And then somewhere here, we also change the Z ordering of these cards during this animation. We have this helper class boundary conditions that basically gets, and this method, get boundary conditions, that returns the boundary condition of the respective card view at the point of interest. And I also implemented very simple interpolator to implement this overshoot throw effect when you throw the card and it initially moves in the direction of the throw, but then reverses and comes back. Not a very good implementation, I admit, but I just don't want to spend any time on this interpolator. It's not important. You can replace interpolators at your will. So that's the implementation using Android views, and as you can see, it's much more involved than the Compose implementation, which frankly was expected. Now let's discuss the various metrics that we can gather from these implementations. To compare the metrics of these two implementations, I'm going to just build a table in which we will have three different metrics. The first one is time to implement. How long did it take to implement this UI element? And for views, I can tell you precisely that it took almost 16 hours. So I rounded up to 16 hours. 2 hours for the UI construction stuff, the card and the stack of cards, etc. And then 14 hours of really difficult slog for implementing the states and the animations, and then a long time to debug everything and cover all the edge cases related to this very complex UI element. For the Compose implementation, I don't have this stat because I've just received this source code. But my estimation is that if a experienced developer would write this code from scratch, then most probably it will be at least 5 hours, probably closer to 10 hours at the very least. Now, since the Compose implementation was based on the previously existing Flutter implementation, and the Compose is kind of Flutter in Kotlin, I kind of assumed that it took them less time because they could just, take Flutter code, translate it into Compose implementation and use it as is. But that's just my gut feeling. If Googlers would like to share with us their metrics, how long did it take to implement this animation, then I will add a comment below this video. So that's the time to implement. 16 hours is like a crazy amount of time to spend on an animation, especially that I'm not going to use it. I don't need it in any of my real professional projects. So it was kind of like very expensive challenge for me, but I must admit that it was really interesting and really challenging. And then we have lines of code. So standard views implementation across those two classes, stacked cards view and card view, uses 550 lines of code, and the Compose implementation implements in 216 lines of code. And you can see that Compose is really shorter than the views implementation. Is it better though to be shorter? I'm not sure. So for example, in my source code, I have all these constants extracted into constants. And inside Compose code, they just wrote them inline inside the codes without defining any magical constants. And I personally think that it's a bad coding practice. So is shorter code better? Well, if it's equally clean, then maybe yes, shorter code is better. But just, by looking at the lines of code, it doesn't tell you anything about the quality of the code or the functionality implemented by that code. And therefore, I present this metric. It's kind of expected that Compose will be shorter because it's much more dense. But I don't think it's actually any better. The Compose code, I don't think it's better than my code. My code is really extensible, really clear, and you can understand, any developer can just jump in and understand what's going on here. But in Compose code, it's like Wild West. Well, at least I cannot immediately understand what's going on there. And then we have a very important metric, performance. Is Compose more performant than the standard Android views? Or maybe if the views are more performant, then by what factor? And this is never discussed, right? You just see all this interesting stuff that you can do with Jetpack Compose. No one gives you the performance metrics, but they are actually interesting and important in some cases, because if you cannot make an animation that renders quickly enough, then your application will skip frames, and that's actually not very good. So render time, how can we measure that? Well, we're going to measure relative render time using the GPU profiler inside your Android device. You can enable that inside developer options. And when you enable this profile mechanism, what you see on your screen are these vertical bars, and the height of these bars represent the time it took to render each individual frame. And you have these three horizontal lines on the screen, and what you want to achieve is that the render time for your frames will be below the green line. That's on my device 120 frames per second. And therefore, let's see how views animation perform. And as you can see, even though here and there we have a frame that takes a little bit longer than required, on average, we are well below the 120 frames per second. And this means that this views animation performs really, really well. And that will be our standard benchmark. That will be 1. I don't know exactly how long it takes. I don't want to measure, the average frames per second. And by the way, this is the release build of my Tech Your Chance application, and we will compare it to the release build of the Compose Playground application. So these are the actual metrics that you can expect to see in release on real user devices. This animation is well below the threshold of 120 frames per second. So let's switch to the Compose implementation. And now let's test Compose implementation. And as you can see, it's much more resource hungry. It takes more time to render. Now, it's not awfully bad, it does not cross this red line all the time. Sometimes it does, but not always. But on average, you can see that there is at least a factor of 1.5 between rendering time of views animation and Compose animation. And mind you, the animation that I implemented using Android views is even more complex than this one, because it also has this horizontal movement. Again, not a big feature, but it still consumes some amount of resources to compute and animate this horizontal movement. And therefore, even though views animation is more complex, more involved, Compose animation still takes much more time to render the frames. And as you can see, most of these frames that we render, well, pretty much all of them are above the green line, and many of them, or even most of them, even cross the yellow line, and some of them even cross the red line, especially when we throw multiple cars into the air. So let's summarize this finding. If we define the frame render time of the views implementation as being just 1x, then the Compose implementation comes in at approximately 1.5 to 2x of that time. And of course, that's something, small little nasty secret of Jetpack Compose. When you use Jetpack Compose, you cannot get the same performance as when you use Android views, classical Android views. This framework is not mature enough to compete on performance. Is it important? Well, I do agree that in many cases, the difference in performance is not important. But in this specific case of a complex animation, you saw that, the frame rate already comes, goes into the red area, which means that we cannot sustain 120 frames per second using this Compose animation. And all we have right now is just this animation. We don't have any other elements. But if you would use this animation in your production app, well, I don't know why would you want to do that. It's completely theoretical exercise in my opinion. But let's say you do want to use something as complex as this animation in your production app, then most probably you will have other content on the screen, and therefore not only this animation would not render in 120 frames per second, but the other content on the screen would probably also suffer. So yes, there is a clear advantage to classical Android view system in terms of the performance, and now we quantify this advantage. At least 1.5x, it's not nothing. And in many cases, especially in the cases of complex animations, and my device is, well, it's not very new, I don't use flagship devices, But there are users out there, especially in lower GDP countries, who have devices much less powerful than mine. And on those devices, using compose animation as opposed to views animation can actually make a real difference to their experience. And voila, now we have metrics to compare the compose and the views implementation of this animation. And well, everyone will surely kind of interpret these metrics differently, but at the very least, we have some metrics. And now I want to jump to one very important point, which I kind of discovered just after I implemented my own animation, and I just wanted to test that it behaves exactly like the Compose version. So I compiled and installed the Compose animation, and then I discovered a little dirty secret, well, not a secret, but maybe oversight, that Jetpack Compose version of this animation is totally broken. So we do not even compare apples to apples here. We compare a perfectly working views animation, very performant, to something that is broken. So let me show you at least two ways I found this Compose implementation is broken right now. All right, if I just, fling one card, then it lands where it should land and everything is fine. And I can actually fling multiple cards and all of them will land as expected in the expected order. But if I now fling the card, which is not the top card in the stack, let's say this yellow one, as you can see, there's something happened there. Now the red cards jumped to the foreground. Let me fling the blue one, and the yellow one jumped to the foreground. But since the blue one was behind the red one shouldn't have been affected by this fling at all. And it's actually getting worse. So we can fling, and now you saw a card falling just in front of this stack. And what it means basically is that the state management, order management, state management of this animation is broken. And I do understand, as someone who spent maybe 4 or 5 hours just on this aspect of this animation, this is the difficult aspect here, not animating a view to rotate. Managing the state and interdependencies between different states, that's the difficult part of this animation. And I spent maybe 4 or 5 hours out of these 16 hours just debugging all the edge cases related to state management. And in this animation, this crucial part is broken. And I understand why it's broken. It's very difficult to get it right. So that's the first bug that I found inside this Jetpack Compose implementation. And there's another one. So if I just, throw cards into the air and keep flinging, you will notice that they do not come back. So there's some kind of something about this animation just passes my actions to the cards which are not in the scope of my kind of touches. And that's of course also a very bad bug that, in my opinion, just makes these two animations completely different. Let me show you my version. Okay, so if I take my version and I fling, then only the cards that I kind of touch will be affected by this fling. And if I happen to land on an empty space, then nothing happens. So nothing of this kind affects my version of this animation. And of course, you can fling any card and the order in which they land eventually will actually be completely correct. And this is what this animation is all about. Understanding where the touches happen on the screen and properly managing the order of these cards after they animate, after and during they animate. That's the difficult parts of this implementation. And I was kind of very surprised to find out that after I spent so much time on implementing it using Android views, that Jetpack Compose version, which I tried to mimic, actually does not do a good job there. And so after I spent all this time implementing this animation using Android views, and you saw yourself that it's much better than the Compose version, I think that I have the moral right to challenge the Jetpack Compose team. Okay, folks, I took your challenge, and by the way, Googler was the one who challenged me to implement this implementation. Therefore, I throw a challenge back at Google. You use this animation to showcase Jetpack Compose, and we know now that it is broken. So fix this animation, that's your challenge, and show us the resulting code. Because all these claims that Jetpack Compose makes it easy to implement animation and it makes the code more maintainable, now you have a real chance to prove that. If you can fix this animation, and for someone who builds the framework, it shouldn't take more than 1-2 hours at this state to fix this element. So fix it, show us the resulting code, let us just see that you can actually incrementally fix this thing, that you don't rewrite everything from scratch to account for these new requirements. Show us that you can do that with Jetpack Compose, show us that you can fix this implementation in a reasonable time, and I totally get why it doesn't work. It's the difficult part here, and I actually spent a huge amount of time getting it right. So I do understand the challenge, and I throw this challenge back at you guys. Go ahead, fix that, show us the code, convince us that Jetpack Compose, your framework, actually can deliver. As far as I'm concerned, the facts are very clear here, and the metrics and the features are very clear that we have a problem. And I think Google should come forward and just, prove that this thing can be fixed and can work reliably. Okay, with that, I constantly, for the previous video as well, I've got many questions. Where's the source code? We want to see the source code. Okay, I will release a tech assurance application. All of this was written in the context of my application that I'm going to release and open source sometime in the future. So when this happens, I will post a link to the application down there, and you can just see the source code. If the link is not there when you watch this video, then I suggest maybe subscribe to my email list on my website, and I will send a notification when the application is open sourced. And in addition to this video, for the Take Your Chance community members, I'm going to record a more detailed code review of the Views implementation to actually deep dive into the challenges and solutions that I implemented, because it is the most complex UI element that I've ever implemented for Android or any other framework, the most complex UI element I've ever implemented. And there are a lot of very interesting stuff in there. So if you are a community member inside Take Your Chance, you bought one of my courses, then we will have this review very soon on our community forum. Okay, that's it for today. I hope you enjoyed this tutorial, and I do hope that Google takes on the challenge and actually proves to us, to the developers, that the framework that they push so hard can actually deliver. And it's not just, a quick way to write broken and non-performant source code. And if they do respond to this challenge, I will post a link to the response. I will describe the response, maybe create another video, reviewing the new implementation, comparing it to the previous implementation, and benchmarking the new implementation as well. And with that, thank you for watching. I'll see you next time. Goodbye.